It's very good to see all of you here today. Hope everybody had a great weekend. This week's subject is going to be a little slower paced than last week, so that's a good thing. You guys have a pretty light reading load this week. We're only doing one chapter, which is pretty short. Next week's going to ramp back up again. And the previous instructor actually skipped chapter 5, which is all about light and how light works. And so I'm not going to put you guys through that chapter because I think you're going to get it in your other classes for the most part. But we will do a little summary of that and talk about it. All right. So today, before we get started, actually, when are all of your quizzes and assignments due? Saturday, yeah. Sorry about the confusion, folks. So I'm still getting used to the Moodle system, but it seems like if I want to leave those open so that people can turn them in late for partial credit, I can't make it close exactly. So don't pay attention to those dates as far as when the quiz is over. Just send them in Saturday night, and everything will be all good. Right. So cool. So we don't have. We're going to do half chapter 4 today, and that part is essentially getting some bearings on how astronomers go about locating stars in the sky and the system of coordinates they use. And then we're going to talk about the nature of the seasons and also a bit about climate, which is a super hot button topic. And it's rather poorly understood. So that's fun because it means we get to explore lots of different theories of what could be going on. So I'm really excited about that. And then finally, we'll talk a little bit about calendars. Everybody has a calendar. I mean, all colleges have had calendars. We went over this a bit in the first class, but I want to talk a little bit about how we fine-tuned our present calendar if there's time at the end. So let's just launch right into it. By the way, I started to get into the relationship between inertia and gravity in the last class. I said I would deal with it later. I was looking over the course material. It makes more sense to deal with that next semester. So if you're really interested in that topic, sign up for the cosmology course, because we'll do general relativity then. And it's a really cool story, but it just takes too much time. I was hoping I could maybe just chalkboard it out for you really quickly, but it's not something you can do really quickly, unfortunately. So we'll have to save it for a whole class, and there just isn't one. So we want to do all the different planets in this class. And after we get through all these basics, we're going to just really start taking a tour of the solar system, making sense of what we see out there, which is going to be really fun. So, but there's no time for general relativity. So last week, just to refresh your mind, we went over the celestial sphere, which is this imaginary projection on the sky of essentially our own globe, which allows us to orient ourselves to the star systems. It all rotates around the poles, right? Just like our planet. We also talked about orbits, which is this very magical, almost, let's say, fortuitous, very, very useful balance between forward motion and inward pull of gravity. Without that perfect balance, everything would not be here. And then we talked a bit about gravitation itself, which we more or less deduced was something like the pull of atoms upon one another. And of course, physicists are trying to apply that to the subatomic world. It's not really working out right now. So we'll leave it at that. Think about it as atoms pulling on one another. And of course, the mass of atoms scales that behavior. So like I said, this week, let's check out how we track things in the sky, the seasons, and then we're going to talk about time. A lot of you mentioned time as a concept. Like you wanted to, in the first video responses, a lot of people said, I want to understand what time is all about. And so we're going to talk about that because it's one of my favorite subjects. But first, let's check out this grid-like system that we use on Earth, because if we can understand the grid on Earth, then we have a better chance of understanding the grid in the sky, which is what we really want to know when we talk about tracking the planets and tracking the stars later in this course. So the grid on Earth is defined by a series of great circles. And what is a great circle? Well, it's a geometric concept, which is essentially the widest points on a sphere. So the one we're probably most familiar with is the equator, right? But you also have, if you draw great circles through the poles, you have essentially an infinite quantity of great circles that you can come up with. And those turn out to be our lines of longitude, or meridians, if you want to call them. So the longitude is defined arbitrarily east and west of a certain point, which happens to be in England. And so if you can see here, they've actually drawn out Washington, D.C. as a textbook. And the basic idea is that it is a certain, 77 degrees west of that prime meridian, right? The meridian that goes, that's the 0 point for the longitudinal system. So why did they choose Greenwich? Because they were at the peak of the imperial world at that time, and they were the deciders, so they said it's here. It's completely arbitrary. So all of the longitudes go either 180 degrees east or 180 degrees west of the prime meridian. And this is the Royal Observatory in Greenwich, which is where everything passes right through. Makes sense. And from this, we can start to understand the concept of declination and right ascension, which is what we're going to actually project onto the sky. So the equivalent of your latitude, and we talked about latitude in the first class, right? This has to do with the orientation of yourself with respect to the horizon and the pole star. The equivalent of that, when you look up at the sky, is called declination. And you can think of it as latitude where the North Star is at 90 degrees. The longitudinal equivalent is a bit confusing. It's called right ascension, which is a very bizarre term. I don't think that it has necessarily anything to do with right or left. However, if we're looking down on the sphere from the outside, you can think of it as being the amount, not in degrees, but the amount of separation from this arbitrary point, which is actually an alignment point, and I'll talk about that in a second, where the 0 point for right ascension is. So for whatever reason, right ascension is measured not in degrees, but in hours, minutes, and seconds. And I think it was the last class where I was talking about how bizarre it is that we use, for the circle, we use a base 60, right? This is strange if you think about it, because everything else in the modern world we use base 10 for. This is inherited from the Sumerians, actually, and I think that at some point I was like, I have no idea why the Sumerians used a base 60, or base 6, or however you want to think about it. Base 60, I guess. And does anybody have any ideas about that, by the way? So I've been putting these lectures online in case anybody misses a class, you want to go find them, get the links in their syllabus. But anyway, somebody else who wasn't even in class watched the video and pointed out to me that it had to do perhaps with the fingers, actually, which is you have three joints essentially on each finger. And so you have 12 total on each hand, which is divisible by 6. It's a theory, it's an interesting idea. If anybody can think of any other ones, I'd like to hear them. So at any rate, the system of right ascension inherited this same idea. And I think this animation should play. Yeah, great. So the right ascension is defined by the point on the celestial equator that rises with celestial objects seen from the Earth's equator. And this is going to happen right where the equator intersects the horizon at the spring equinox. And we're going to talk a bit about what the spring equinox is in a minute. But very arbitrary point, but it happens to be in the same place every year, and we can measure where that is. And actually, we can make a star map, which I'll show you in a moment, of the entire sky based on that, and keep track of where things are on it. So let's check out how you do that. So in this case, what's very strange is when you look up at the stars, the right ascension actually moves to the left, right? Because you're inside of that sphere now. Now it's looking at it from above where it would be on the right. This is how I think about it anyways. In this case, we're trying to pinpoint Sirius, which is actually at a declination of minus 16 degrees, right? It's down below the ecliptic. And we have the right ascension of 6 hours, 45 minutes. So this is the kind of map that you can create from that, which is pretty cool. And these are, you'll see these, if you look, actually, even the ancients had some semblance of a similar map of the sky. I didn't use this exact terminology, but it wasn't so far off either. So in this case, you see the plane of the ecliptic, which is basically where all of the planets and sun is, for that matter, for the most part, within a matter of degrees of the ecliptic. That's the plane in which we're all existing. And then you can see the equator there, which is I believe in green. And then all of these lines, the longitudinal lines, are right ascension lines. So this is something you just need to tuck away in your memory, because we're going to come back to it over and over again later when we talk about various positioning of bodies. All right. Now, I'm going to switch gears a little bit, because we need to talk mainly today about the motion of the Earth. This whole discussion is going to concern all the interesting ways in which the Earth moves. Because up till now, we've talked a little bit about the Earth turning. We've talked a little bit about the Earth as it orbits the sun, but there's a lot more to it. In fact, there's so much more to it that we don't really even totally understand all the ways in which the Earth moves. And that's really cool, because that means there's a lot of work for you to do if you should choose to go into any of this. Now, it might be taken for granted that the Earth is turning. Most ancient peoples seem to have, at least in some corner of their society, understood this. However, it wasn't actually really established empirically until the 1850s. And so have any of you seen these pendulums before? Yeah, they're at most science museums. Do you have a question? No. Okay, just joining in. Yeah, they're pretty cool, right? So this was the first time that somebody actually demonstrated the turning of the Earth. And it's a pretty simple idea. I meant to bring something to use as a pendulum. We'll use my car keys. But essentially, if you're in a completely still reference frame and you start something swinging back and forth, it's just going to swing like this, right? But if I start moving, right, if I have some sort of motion to me, then the pendulum is going to turn in a circle. It's going to precess. And so this gentleman, Foucault, proposed that this is exactly what would happen if you built a big enough one. And he did so. He built it in the Pantheon of Paris. And he started it up, and lo and behold, it worked out. And people have replicated this all over the world. And it's a pretty cool demonstration of the turning of it. So they let this thing go in the morning. I don't know how often they let it go. Let's say in the morning. And it precesses and proceeds to knock down one of these little pegs at various hours of the day. It's a very predictable motion. So that's a little cool aside about how we can understand exactly, if it's not apparent to you that the Earth is turning from watching the sunrise and so forth, this will do it. And here's a little schematic of that. I should have shown that earlier. Now, I want to talk about time in a second, but we keep time with, you can use a pendulum, you can use a clock, you can use anything you want, as long as it's regular and periodic. So what is time exactly? This is a pretty huge question, actually. And it sends people into all sorts of catastrophic tailspins trying to parse it. Time in terms of fundamental physics comes down to what clocks do, which is really fascinating because not all clocks do the same thing, right? If I have a sundial, which we'll talk about, I can very regularly tell you whether it's noon or midnight. But if I take my sundial inside, it's not going to work very well anymore. In fact, it's going to give me false information. And it turns out that this is actually the case with all clocks. And this is very frustrating because it's led to a lot of mystical interpretations of what time is, in my estimation. So, you know, we probably, and we'll do a lot more of this in the cosmology class. I really hope you guys will take that one. But, you know, one consequence of general relativity is that when something is near a large gravitational body, that time is affected by it. And they can do fantastical tests of this, right? They'll send these satellites up into orbit. And, well, they actually had a satellite that was broken when they first tested this. And the satellite was supposed to be orbiting at a constant distance from the Earth. But it failed for whatever reason. I don't know what happened exactly, but it started orbiting with a high eccentricity, right? It was very elliptical. And they had an atomic clock on board. And we'll talk about what that is in a second. But they noticed that the time was actually changing as it got closer to the Earth. And you might say, well, okay, time is being affected by gravity. And this is perfectly true. It is, because you've defined time as what your clock is doing. But you might ask yourself, why is the clock behaving that way? For instance, what if they'd had an hourglass that they took up into space? It wouldn't work at all, right? And it's quite interesting. You can they've measured clocks. Usually they use these atomic clocks to talk about that. And they'll take them up very high, and they'll see that time is actually moving differently, right? And it's actually moving faster away from the Earth, time, as measured by these clocks. And this seems very spooky and so forth, right? Like, you know, it's going to, you're going to maybe experience things differently than somebody else on Earth. And there may be some truth to that. But in reality, let's think about what these clocks are doing. What's an atomic clock? It's the most precise clock that we have. Sounds, anything you put the word atomic in front of is quite, you know, precise sounding, right? But what's an atomic clock? It's, yeah.
An atomic clock is I'm going to use what my friend once used to describe it, a clock that is as big as a semi that really accurately keeps track of time.
Yeah, that's how most people understand it, right? It's a very expensive clock, right? But here's what it is. It's a very refined crystal of a particular atom, in this case, cesium. And atoms vibrate. That's not quite the right word for it. It has a different name, but let's think of them as vibrating. They pulsate, right? They do this thing called a quantum jump where they pulsate. And as they pulsate, they give off light. This is when they're jumping between different energy levels, right? You've probably seen this on the schematic diagram of the atom, where it's going between different orbital states or different energy states. But at any rate, it does this in a predictable fashion when it's energized appropriately. You know, they'll give it some voltage or whatever. So it pulsates at a particular rate, okay? The atom is pulsating. Now, if you think about gravity as atoms pulling on one another, it starts to make a lot of sense why, if atoms are very close to lots of other atoms, they're going to be pulled on a lot harder than they are if they're farther away from other atoms, right? Especially if there's a radial architecture to this, as we talked about with gravitation in the last lecture. So all this is to say that it's not unreasonable that the clock should be affected by gravitation. This doesn't have to involve some sort of magic or spookiness to it, although it's completely consistent with all of the interpretations that you'll hear in the popular science world. So anyways, I put a little blog about this in the lecture notes this week, and you can read more about it. But it's a fascinating concept to think about. The time is what we can measure. Now, what are we measuring, right? Time is what clocks do. And this is actually a famous quote from Einstein, that time is what clocks do in physics. So that's a really scary concept because clocks behave differently depending on where they're at, right? Fortunately, for everything that happens on Earth,
I would thought a couple of years ago you could find second as a certain distance that light travels.
Yeah. Mm-hmm.
You know that,
Mm-hmm.
but that wouldn't be affected necessarily by gravity on Earth. It's still in a vacuum.
Well, you wouldn't think so. Well, on Earth, no, right?
On Earth, yeah.
So
Hypothetically.
you're absolutely right. Yeah. So, well, this goes back to how you define mass and so forth as well, too, right? Actually, for a while, they defined mass by they literally had a kilogram, right? And they would keep this in some vault somewhere, right? And every time they move the kilogram, this is the master kilogram, right? They'd have a guy walk behind the guy who's carrying the kilogram to catch it if it falls, right? Because they can't lose the master kilogram. And of course, it can be defined in terms of water and so forth, but these things are subject also to location. And light and time was much the same way. So they reoriented things in terms both mass and light in terms of electrical signal, which is a whole can of worms. Again, come to the cosmology class. I think we'll have more time to get into the nitty-gritty of that. But the issue is still, if light is being used to define time, and light is defined by wavelength, which comes down to the pulsation of atoms, like you don't have light without atoms. This is something that is lost on most people. I think that I don't mean to sound condescending, but I think it's lost on most physicists as well. You don't have light without atoms. Okay, you need an atom to receive the light. You need an atom to emit the light. It's just inconceivable otherwise, right? So it's coming down to everything about the phenomenon of light is coming down to behavior of some material object that's doing something to some other material object. And the specifics of that are far beyond the scope of this course. But they are subject to gravitation, and this can get a bit tricky to parse. But let's get back for a second. So, what is a clock actually doing? What's happening here? Like even on this clock over on the wall, like what is it doing?
It's measuring a progression through space.
Through space.
Or it's measuring a progression.
It is measuring a progression. Oh, that is absolutely right. It's measuring change, right? It's predictable change too, which is what's really important. And I think this is probably the best definition of what a clock is. It's a regular periodic motion, right? And so, to some extent, where do we get our time system from? Well, we get it from both predominantly from the rotation of the Earth, right? We have a new day, right? Which is just the period of our rotation. And then we can cut that up into whatever units we want. Again, the base 6, which is quite fascinating, is cut up into 24 hours, which seems quite arbitrary, but it made a lot of sense to the Sumerians for whatever reason, I'm not sure. So we have this predictable periodic motion of the Earth, and this is our basic clock actually on Earth, and it's been the basic clock for human beings for certainly thousands of years, if not longer, since people started thinking about the fact that tomorrow is going to happen. It's going to happen in a very similar way as today. It's hard to tell how long humans have been doing these kind of things. Maybe we've had fire for 50,000 years. There's some evidence of that, but I think people have been studying the stars and thinking about time for much longer than that. Certainly, you can trace humanoid-like beings, entities back perhaps millions of years. So clocks are giving us this predictable periodic motion that we can assess the rate of change of other phenomena by. And, physicists are very uncomfortable with that. And actually, several folks, very brilliant folks, have tried to escape this idea. They bring in the concept of entropy. Does anyone know what entropy is, essentially? Oh, that's a good word, worth learning. So entropy is essentially the tendency of things to fall apart. It's a tendency towards chaos, right? Which is lack of orderliness, right? The opposite of cosmos. And so there's some, if we're talking about the rate of change of something, there's a predictable rate of change, particularly with particulate systems, right? You take a gas or something and you put it in a container, it's gonna have a tendency to spread out and cool down, right? And so this idea of being able to clock things by their tendency towards entropy has been attempted by various physicists over the years. It's not perfect, there's problems with that too. I mean, given a long enough time, if I put a bunch of molecules in a container, you would say, okay, they're all gonna spread out and cool down eventually. And it's like, fair enough, they probably are. But what if you wait even longer? What if you wait almost forever? What will happen? Well, at some point, they're probably all gonna be in one corner of the box, actually. It's just statistically inevitable. It must happen at some point, right? And so entropic anomalies do happen, and this presents problems for defining time in terms of entropy. So what I think that we should really do is think of time as this the motion of some body with a memory of where it used to be. So time is a very human concept. You can't have time without memory, right? There's this famous cognitive neuroscientist named Oliver Sacks. Anybody heard of this guy? Oh, he's a very, very interesting guy. You should read his books. But he, and I had a chance to meet him actually and hear him speak. He came to my college when I was younger. He did all these wild case studies where he would look at people whose brains were damaged in various ways. And there were certain individuals who had lost portions of their brain that were responsible for memory. And these people had no sense of time whatsoever. You could say something to them, they'd be very friendly perhaps, and then 5 seconds later they'd be introducing themselves again, right? They wouldn't know what day it was, what time it was, anything, right? So time comes down to the motion of some body, plus a memory of where it used to be, and that's essentially what a clock does too, because if you look at that clock and you don't have any idea of where it came from, it's not going to be much use to you. Questions about time? All right, before I depart. Okay, we can come back to this. We're going to do a lot more of it in cosmology too. So the length of the day is obviously the rotation of the Earth. Now, there's 2 ways to think about the rotation of the day. One's called the solar day, which is the one that you're familiar with. That's when the sun rises and sets. And then there's the concept of the sidereal day, which is the rotation of the Earth with respect to the stars. And you might think that they're the exact same thing, but they're not quite the same thing, because the sun is actually, well, not the sun, sorry, the Earth is actually orbiting the sun. And that means that every day it's actually getting a little bit closer in one direction, right? By about a degree on day 2. And that means that the solar day, the one that you experience, is actually a little bit longer than the sidereal day, because you're experiencing a little bit more sun each day, because it's turning into it. It's turning away from it. So to complete a solar day, the Earth has to rotate actually an additional 1/365th of a full turn, and that's about 4 minutes. So we set the sidereal day right at the vernal equinox, just like we do with the right ascension, and we'll talk about that. That's essentially the moment when both hemispheres are illuminated equally. This is in March. So the apparent solar time is not quite perfect. And this is one of the reasons that we prefer the sidereal time. Actually, when people began to have mechanical clocks for the first time and stopped using sundials, they noticed that there were some issues. And this actually has to do with the way that the Earth varies in its elliptical orbit. It's not quite perfect. And the Earth's axis of rotation is also not perpendicular to the plane of revolution. So the solar the solar time, even as it is off, is not off at the same amount each day. So this is problematic. So what we do on Earth is we come up with this concept of mean solar time, which is the average of the solar time. And mean solar time is not entirely convenient, because if we all went off of mean solar time, by the time that you traveled across town, you would be off by a few minutes from somebody who was, let's say, on this side of town. If you had a meeting with them, you would never be able to make it, right? Because noon in your mean solar time would be different than their noon, even a few miles away. And actually, what's fascinating is the way people got around this until very recently was they just came up with their own clocks for each town. And so this is, if you look at old villages, especially in Europe, you'll find a clock being centrally featured in each one of the villages, right? And that's because that was what time it was in that town. And it wasn't until relatively recently that folks began to try to standardize this across the globe. I think it was probably in the late 1800s. In fact, well, today we have these time zones, right? And this is also quite funny too, because as you can see, the time zones are, and this is obviously, the concept behind this is we just divide the world up evenly so that the mean solar time can be standardized across at least your neighboring towns, right? So at least you can go to the other side. You can go to Grants Pass or something, and it's not going to be a different time. It's terribly inconvenient. But what's really funny about this is that certain countries didn't want to mess with it, right? Like India decided to have 1.5 time zones, and China decided to only have one time zone for its entire country, which is quite fascinating because it means, like, if you're in Tibet, it's already almost noon by the time the sun is rising, right? Which is pretty crazy. So anyways, we concocted the time zone system to get around this problem. And for the most part, it seems to be working out. And then we had to draw a date line somewhere, right? This is quite fascinating. Otherwise, people would be in the wrong. They'll think it's the morning. Yes.
Do you think that Hong Kong is like in the same kind of time zone, or do you think they have like a different one?
Ooh, that's a good question. Can you see it on here? Yeah, I don't know. Google that. Let us know. This is an interesting question. I think you say Hong Kong because it was at least, I'm not sure what its political status is right now, but it was a British protectorate for most of its history.
Yeah, that's why I was.
Yeah, I would imagine that they went with the time zone most proximal to them, since it seems like the Brits set up a lot of this stuff, actually, which is fascinating. It's hard to overemphasize how dominant the British imperial structure was on the rest of the world, especially during like the land grab of the colonial period. I mean, it's funny because there's this tiny little island, right? But they were essentially the United States before the United States. They controlled a lot of the trade, and they were enforcing their language. Obviously, we speak their language. So does a lot of the world. So we had to draw a date line too. And the interesting thing is they put the date line right in the middle of the ocean, which is probably a good thing, because if they put it right through the United States or something, we would have 2 different days going on. And of course, completely arbitrary. But this makes sense to put it through the ocean. And it accomplishes it such that neighbors don't have different days. So let's talk about, anybody have questions about the timekeeping system that we have, which is arbitrary but useful. It seems to have been refined over many years. Cool. So let's talk about seasons a little bit. we went over this a bit in the first class, but I want to make sure that nobody walks out of this course without understanding how seasons happen. So, contrary to popular belief, seasons have nothing to do with how close the Earth is to the sun, although that appears to matter a lot later on when we talk about climate, which is essentially a bigger pattern of weather. The seasons are an intermediate pattern of weather that change every year. And the seasons all come down to this axial tilt, which means that our planet is tilted slightly, about 23.5 degrees, off of its orbital plane, which is, of course, the ecliptic. We talked about that before, too. And so when up here in the northern hemisphere, when it's warm and sunny in the south, and our partner latitude, let's say somewhere in Shilo or something, it's actually quite cold, because as that Earth is rotating, the northern hemisphere is illuminated in the south. It's dark. And so it turns out that there's a moment where it's about the same for everyone. We call these the vernal and autumnal equinoxes. And this is why we calibrate all of our ascensions and all of there's so many different calibrations that occur on the equinoxes. For whatever reason, they use the spring equinox by convention. And so it's also actually worth mentioning that at this exact moment in time, the perihelion, that's a word you could impress your friends with. This is the closest point that the Earth gets to the sun. Remember, the Earth has an elliptical orbit, although it's very close to a circle. The eccentricity is very, very low, but it changes, and we'll talk about that later. But actually, the perihelion actually occurs in January at this moment. The closest moment to the sun is actually it's quite cold for us. It's quite warm for people in the south. Okay, so there's something else to this story, which is that when the Earth is tilted, when you're tilted away from it, let's say in the winter for us up here, the illumination from the sun is actually coming in at an angle. This contributes to the cooling effect as well, and people often don't think about this one, but it's quite remarkable. So what you actually have is each one of, you can think about light as rays. I don't think that's an inappropriate way of thinking about it. And hopefully next week we'll talk a bit about what light is. Right? We talked a little bit just now about light being a conversation between atoms. I think that's appropriate. But what happens when the sun is at a greater angle, let's say a more oblique angle, in this case between summer and winter, we go from 73 degrees to 26 up here. These rays are actually spread out quite a bit as well, which lowers their intensity on any given surface. We also have atmospheric effects too. So we'll talk about that when we get to climate, but there's quite a bit of refraction in the atmosphere, right? The light has to go and bounce through, see if that's a reasonable way, or let's say relay through all of these atoms on its way down to us, right? And many of them are optically transparent. Actually, it's quite fascinating. If you look at the absorption of the atmosphere, like what color of light does the atmosphere take away from us? And by light, I mean all radiation, from X-rays to radio waves. It's all light to me. It's all radiation, right? If you look at what is transparent to what light actually is relayed through the atmosphere, not much is actually. A lot of light is absorbed by those atoms. The light that's relayed through happens to be perfectly in the visual range, right? The colors we see with our eyes, it's perfectly transparent to those, and it's perfectly transparent to a few different wavelengths of infrared. There's some notches up in the radio wave spectrum, but generally speaking, the atmosphere is very opaque. It interacts with light tremendously. And so that has an effect. It scatters light in an interesting way, and it does more so when it comes at an angle because it has to travel through a greater volume of atmosphere. And so this is also contributing to the cooling effect during the winter as the Earth is turned against us, rotated, tilted against us. Turned against us makes the Earth sound evil. Sorry about that. So let's see. This is maybe worth looking at. This is from your textbook. I'm not a huge fan of this picture because it's horribly exaggerated, but you can at least get the idea that the sun's path in the summer for us up here is quite high in the sky, whereas the sun's path in the winter is quite low. This varies by really a matter of degrees. It's not as extreme as it shows here. And the consequence of this is just as we've shown, that at the higher latitudes in the summer, you actually have sunshine reaching the polar areas in the Arctic all of the time, right? This is quite fascinating. And likewise, in the winter, they're going to be dark all of the time. I want to show you a movie of this in a second. It's really something to see. And this is actually where we come up with the concept of Arctic Circle from, right? You can go and tell your friends about this later too. The Arctic Circle is defined by that region which is capable of receiving 24-hour sunlight in the summer. And the Tropic of Cancer is defined, there's also a latitude point. You can see it, I think, on this, yeah. Which is defined by the sun being directly overhead on the summer solstice. So these, we talked about the equator, but these are the two other main points that you need to understand. And of course, the reverse is true for the southern hemisphere. I'm not going to talk enough about the southern hemisphere. It probably won't matter to most of us unless we travel down there. But perhaps they teach astronomy in reverse in the southern hemisphere. But whenever I refer to these things, I'm going to be talking about the northern hemisphere. Okay, so, of course, this is the summer down south. You see the same thing. The Antarctic Circle is exposed to sunlight 24 hours a day. And this is what it looks like. Hopefully this will play. Come on. Oh, here we go. Play. So this is in Norway, and this is the same place, but we're looking at the summer solstice on the right, and the winter solstice, respectively. And you can see this is a full 24 hours. And I don't know if you guys have ever known any people who lived in these latitudes, but oh, there it is. For just a second at noon, the sun comes up for a second there in Norway because it's not quite up there in the Arctic. But for the rest of the time, it's pitch black. And as you can see, on June 21st, the sun never sets, essentially it does for a second. Now, it can get really depressing for people who live out there. I had a friend who lived in Norway, and it was very, very, very difficult in the winter because, as you can imagine, your brain just wants to sleep. And this is what most animals do, which is quite fascinating, actually. It's interesting to think about what our ancestors might have done differently in terms of their rhythms in the winter versus the summer, and how those have perhaps been lost in our modern society where we're running on digital clocks and electric lights. But this is quite fascinating. And then one more thing I want to show you is the picture of the. Oh, here we go. No sound, please. This is at the North Pole, essentially, close enough. And you can see the sun as you track it in the summer, never sets. Which is pretty cool. So 67 degrees north is the highest latitude where the sun can be seen for a full 24 hours. And they often call this the land of the midnight sun. All right, and then we talked a bit about how refraction can affect the temperature on Earth. It turns out that it actually affects how we see the sun too. It actually makes the sun appear to rise a little bit earlier and set later than if there was no atmosphere. And that has to do with the actual lensing of this light through the atmosphere, which is something that plagues astronomers because, of course, the apparent location of anything that you see in the sky is subject to all sorts of corrections, not the least of which are atmospheric. And this is why we had very imprecise understanding of our place in the galaxy and really outside of the galaxy until we were able to send telescopes into outer space. Because from Earth, you have to find a desert, you have to find a place that's really high up. In fact, today, a lot of the Earth-based telescopes are found in the mountains, in the desert regions down in, let's see, there's a number of them down in South America in the high desert. There's some in the States, in the Arizona, New Mexico, Nevada area, because you have less moisture, which means you're going to have less atmospheric interference. But this turns out to really affect our perception. And so at the equinoxes, we have to adjust. Actually, the sun is above the horizon for a few minutes longer than 12 hours, even at the equinoxes, which is a bit confusing. So our perception of the equinoxes is slightly different, perhaps, than our modern sidereal interpretation of it is very different than what the ancients probably had. Not very different, but a few minutes different. And then when we start talking about the warmth and the cooling in the seasons, we have to consider this effect. So you've probably all noticed this before. The summer solstice, which is June 21st, doesn't actually appear to be the warmest time of the year, right? We all know that it's actually much warmer in July and August for the most part, right? And so why is this? Well, this is an important concept in physics in general, which is called hysteresis. That's another good word to impress your friends with. Hysteresis means there's a lag time between the impulse and the effect. And in this case, and we always discover these things, these hystereses, before we understand what they mean. And we'll encounter a few more in this course. But in this case, this has to do with the fact that you're actually warming that atmosphere. It's trapping heat. And it takes some time to build that temperature up, right? Everything's melting, thawing. There's a great deal of heat that builds up within the materials. Heat itself, I think, is worth talking about for just a second, because I don't know if you'll get this in your other classes, but heat for most of human history was thought of as a substance, actually. And when I say most of human history, I mean until like 150 years ago. And this is quite fascinating because we all know, as scientists, we understand that heat has to do with the motion of molecules and atoms, right? When they're moving fast, they have more kinetic energy, they have more punch, and so we perceive a greater temperature. But this wasn't the case for most of human history, and even for most of modern rational, even after the Enlightenment, we treated heat as a substance. And why is that? Well, it turns out it works really well to treat it as a substance, actually. And that substance was given many names over history, but most recently it was thought of as the caloric. So there was a little particle called the caloric, which carried heat. And I would say that the preponderance of our thermodynamic theory that we use today, in fact, the people who were working on engines back then were perfectly capable of describing nature with high precision using this concept. Now, this reminds me a lot of our modern concept of particle physics and particles in general, because you ask yourself, what is a particle exactly? Right? And you probably think, oh, it's a little thing of dust or something like that. But when you drill down into it and you really start to understand what a particle is, it's actually just a measurement at a particular location in space of some phenomena. So whether that's an electrical phenomena, whether that's a radiation phenomena, whatever it is, it's a point where a measurement is taken. And the caloric was exactly the same. It was a point where a measurement was taken. And you can watch the flow of these points, right? And, you know, I think we would still be using the caloric much as we use the electron today if it hadn't been for a really cool experiment that this gentleman, Count Rumford, happened upon. So I believe that he was either in the army or he had some pals that were in the army, I can't recall. But he was working with cannons. And he noticed one of the big problems with cannons, actually with guns in general, if any of you are hunters or anything like that, is that the barrels heat up if you use them too much. And you actually have to, especially in war, you have to change the barrels out regularly because they'll melt, essentially. And cannons were no different. This is a huge problem. Cannons got really hot. And so, you know, Count Rumford thought about this a little bit, and he was like, where is all of this heat coming from exactly? Where are all these caloric particles coming from? So he went back to the factory, and one of the points where they actually make these cannons is they use a huge drill and they bore out the holes in the center. They have this huge column of iron and they drill out the center for the cannonballs to fly through. And he studied these construction processes for a while, and he realized that you could generate heat indefinitely, actually. As long as you spun that drill blade, it would just heat up and heat up and heat up. You could actually isolate the cannon completely from the environment, and you still generate heat. This is crazy, right? So if heat is actually a substance, where is it coming from? Now, I would love to see an experiment. I actually dream of doing this experiment with electricity as well, because it'd be interesting to isolate, you can generate what's called triple electricity or friction-based electricity by rubbing something against another surface, right? You've probably seen this before where you like stick a balloon to your head or something, right? If you rub it on your skin. Would we be able to generate infinite quantities of electricity by rubbing it against another substance if it was electrically isolated? No, an interesting experiment. So anyways, that killed the caloric. The caloric was over, and people had some, there was some hints that perhaps heat actually had to do with the motion of molecules. And eventually we were given the kinetic theory, well, the kinetic theory of gases arrived earlier, but it was not really accepted until this experiment was done. And at that point, we started thinking about heat as actually the motion of molecules. So the molecules got to get moving before the heat shows up on Earth, right? The radiation can get those atoms pumping, it can get them dancing around, but you have to accumulate that motion for a while, and so we have this hysteresis. So there's a number of reasons why it's warm in the summer, and none of them have to do with how close it is to the sun. Cool. Questions about that? All right, so let's play with the concepts of climate for a little bit. And this is a really fun part of this lecture because we know so little about it, actually. And it's such a charged subject, right? Right? You talk about climate. I run a YouTube channel, right? I can hardly mention climate, even the word climate, without getting a little notice hung on my videos that says that, climate change is real, which of course, this is obvious for anyone who's studied the history of the Earth's changes, but people are very uptight about it. And why are they so uptight about it? Because we want to protect the Earth, and we're really worried about the Earth, right? And the concept of climate has become interchangeable with the concept of pollution. Now, I think this is a terrible disservice to the world, actually, to be too tied up in the association of these two ideas. And why is that? Well, it's not because I don't think that the climate is changing, and it's not because I don't care about the Earth. It's very much because I care about the Earth a lot, actually. I care about our backyards, but there's a lot of terrible pollutants that are out there that aren't being taken into account. there's no fish left in the rivers, right? Anybody fish? There's just less fish every year, right? It's quite depressing. The animals are disappearing, the bugs are disappearing. Now, the animals and bugs and fish aren't disappearing because of the climate changing due to the changes in the gases in the atmosphere. They're changing because there's a tremendous amount of like thousands of different pollutants going into the groundwater, into the air at all times, right? And if we get too fixated on this concept of carbon, we're going to miss these things that are happening, which are really important, and it worries me a great deal. And so we're going to talk a bit about climate change. And climate change is a really fascinating topic, but it's separate from the idea of taking care of your backyard and keeping your house clean, which is really tragic. I mean, I saw this study, I can't recall the exact specifics of it recently, but they looked at salmon in the river in Oregon, and they found that the salmon had all these little pieces of our car tires in them, right? And if you think about it, I'm driving down the road this morning to get here, and there's friction happening between my tires and the road, and there's little pieces of my tire flying off, and they're going into the ditches, and they're flying off, and they're going to end up in the groundwater. They're going to end up in the river. And this is just one pollutant. Does anybody know what tires are made out of?
Rubber, petroleum.
Yeah, they're not made out of rubber anymore. Yeah, unfortunately, maybe. Because rubber is a natural polymer that comes out of trees. And, perhaps that would lead to problems too. But they're made out of petroleum. That's right. Almost everything's made out of petroleum, actually. This desk I'm sitting on is made out of petroleum. Chairs you're sitting on are made out of petroleum. This fabric's made out of petroleum. Maybe some of my clothing is made out of petroleum. And petroleum is a really highly reactive hydrocarbon system, right? It can interact with your molecules. It can steal little pieces of your molecules. It can take their energy up. It can affect them. And this is really bad for life, actually, right? So we have all sorts of terrible epidemics on Earth right now. We've done a lot for infectious disease. That's actually one of the greatest triumphs. And, you'll always hear from the medical establishment all the time, like, we've eradicated all of these terrible diseases, and it's true. But we've actually promoted a number of other ones, right? The cancer epidemic is quite a tragedy right now. I'm sure, I think something like 1 out of every 2 of us will be affected by cancer in our lifetimes. That's really crazy if you think about it, and it shouldn't be the case. And why is that happening? There's some animals that don't get cancer at all, and we're trying to understand who those are, like the naked mole rats. But until we figure that out, until we figure out how to reverse cancer, we should probably think about how to prevent it as well, right? And this requires us to really think beyond the simple concept of carbon about what's happening to our environment. Carbon's a really easy thing to buy your way out of, right? And carbon matters a lot. We're going to talk about how carbon dioxide affects the climate in a second. But it's a really easy thing to mitigate if you're a company, right? Let's say you're a terribly polluting factory, right? You're putting out thousands of carcinogenic chemicals into the environment every minute. Well, it's very easy actually to scrub the carbon dioxide from your towers. It's actually a very easy reaction to produce. And at the moment, if we are monolithically fixated on carbon emissions at the exclusion of everything else, then these very powerful and wealthy companies have the ability to essentially buy an indulgence. Does anybody know what an indulgence is? Right? They're able to buy their way out of it. An indulgence was essentially something that the Catholic Church had imposed for many hundreds of years, where if you're a wealthy person, you could basically buy a ticket to heaven. Really. Give the church some money and they say, hey, you're cool, you're good to go. It doesn't matter if you've been abusing your slaves or whatever. Okay. Any questions about that? All right. End rants on pollution and so forth. But it's something to really think about as you go through the world and think about all of the things we're not necessarily fixating on that aren't coming from the corporate-driven media about what we're doing to the earth. Because there's a lot of bad stuff that's happening that's not being talked about. And I hope that your generation can grab the wheel on that a little bit and rein it in, because otherwise the very wealthy corporations are going to keep buying those indulgences and they're going to keep telling you everything's cool, and it's not cool. All right, so there's some of these processes we talked about. This is essentially has to do with the heating of the atmosphere. And we can actually look back into time and see how this has occurred. Now, let's just talk about this. This is something you probably heard this talked about as the greenhouse effect, right? Does anybody have a greenhouse when they're growing up? Okay, cool, nice. I want one really badly. Don't have one. Maybe I'll build one. But the essential idea is that it lets in a lot of the solar radiation and then traps that heat. The air stays warm and stays warm due to this greenhouse effect. And of course, carbon dioxide, methane, these entities have the ability to act as essentially a roof that will allow the radiation in and it will trap the heat below it. And so, this is playing a huge role in climate, which is this bigger pattern. But there's a lot more to it than that. And we can actually go back into time and look at how the climate has changed over the years. And we do that with something called ice cores, which is what this person is holding here. Essentially go up into these glaciers. And these parts of these glaciers have existed for hundreds of thousands of years, maybe millions of years. It's hard to say really. They've only drilled down so far into some of these. And what you can see is that there's different layers for each year. They form these little rings, and they trap gases within them. And by analyzing those gases, we can get an idea of what the atmosphere was like going back many, many thousands of years. And the project is, by the way, is called APICA, which is what's analyzing these ice cores, and they're still very hard at work today. And what they see is something like this. So this is a very anxiety-inducing graph. But if we slow it down a little bit, it's pretty cool. So what we have here is years before present, BP. Right, so we're going back and we're looking at a number of changes throughout time. And the one that we're most interested in immediately is the temperature readout here. Because you can see that the temperature changes on Earth over many thousands, hundreds of thousands of years have this predictable rhythmicity to them, right? Much like the rising of the sun every day. There's a spike in temperature every 100,000 years or so. And there's a lot of intermediate spikes. And what's really fascinating is that we see accumulation of ice in these trough periods away from the peaks, right? And these are what we call the glaciation periods. So you can't actually measure temperature directly. And this is where things start to get a little bit murky, because the best we can do is make an indirect readout of temperature. And so this bottom field down here, I think it's like a brownish orange color on the screen anyways. The top one anyways, it has a particular isotope of oxygen that they're measuring, right? And what's an isotope? Does anybody know? So an isotope is it's a version of the same atom, but it has a slightly different weight, right? So the idea is that when it's when the water evaporates from the oceans, the heavier elements are going to be less likely to evaporate. And then likewise, when it precipitates in the north, the heavier ones are going to preferentially, when it's cold and they precipitate out, they will fall first. And so by measuring this particular heavy isotope, we get some sense when we compare it to the ocean standard of what the climate was like at the time. This is very indirect. And actually, as you can see, the oxygen isotope track is not, we're of course comparing this brown one, the second brown line from the bottom, to the temperature readout. It's not perfect, right? It correlates very nice. The peaks are often the same, but you don't see the extremes as well. So there's a lot of guesswork going into this, and what they're doing is they're sewing all of these different traces together. So we also have data here from methane levels, which we can get from bubbles in those ice cores. We also have CO2 levels. And we're able to, with some degree of certainty, stitch together what we think the temperature was over those years. And of course, the glaciation periods are evidence because there's very thick ice there in those times. So we know there was glaciation occurring as well. Now, what we don't totally understand is why this was happening. And there's a number of cool guesses out there. And a lot of them are substantiated, but none of the theories align perfectly. And that's what's really cool. So there's a ton of work to be done in this if anyone wants to get involved. And, you know, I want to show one more thing on this graph, actually. So the reason that people are very much up in arms about CO2 right now, with respect to the greenhouse gases and stuff, is that if you look at the CO2 trace, this 0 point, by the way, is somewhere in the early 20th century. I can tell you, I think it's the 1950s. But if you look at the blue trace, which is CO2, it's pretty much off the charts right now. It actually is off the chart right now. Okay. Methane as well. It's even higher off the chart, actually. And, you know, some people are actually working on methane control. And the idea is that people are very terrified, and perhaps reasonably so, that if these greenhouse gases, as they're called, if they continue to climb, then, you know, we're going to find ourselves in a situation where we don't have polar ice at all, or perhaps not as long as we used to. Now, this is all very complicated because it actually seems like the Antarctic ice sheet is growing right now, which is contrary to this idea. But certainly emissions, carbon dioxide seem to be ramping up, right? This is something to pay attention to, and it's not unreasonable to take carbon emissions as a proxy for, carbon dioxide as a proxy for emissions in general, right? Which we've already talked about. Emissions are full of heavy metals and all sorts of terrible things. And so it's not an unreasonable assumption. But this is what people are very concerned about right now. And I think that's not totally unreasonable. This is actually a picture over the past couple thousands of years of the CO2 levels. And you can see that it's gotten quite extraordinary recently. Now, again, this is by analyzing, you know, the data on the far right-hand side is actually taken with sensors in the atmosphere at present. The data that's taken in the past is taken indirectly from bubbles in the ice cores, which one can imagine might have problems associated with it as well, right? It's very imprecise, but you get the sense that things have been changing recently, and this makes sense. We've completely re-landscaped the Earth since the dawn of the Industrial Revolution. But what's really interesting is that if you look back millions of years, this is going back into the same ice cores as far as we can, we see a great variation in carbon dioxide. Look at this. This is quite crazy, actually. In fact, it seems to be that the variation over the past 500,000 years has been extraordinary compared to most of recent history. So this is something to keep in mind. You know, there's something else going on here in addition to whatever humans are doing to mess the place up. There's something that's been going on for a long time. These excursions have been amplifying for quite a long time. So what is going on exactly with these glacial cycles? Now, this is where things start to get really kind of interesting and fun. The predominant understanding is that a lot of different things are happening right now. And as you can see, these glacial cycles are very predictable going back, and they seem to last about 100,000 years. And it looks like we're in one of these very warm periods right now. And so the question is, will we experience another glacial period at some point? Where will our children experience it? You know, I mentioned last time that I do a podcast, and I had Gavin Schmidt on the podcast. My wife and I had Gavin Schmidt on the podcast, and Gavin's one of the biggest figureheads in climate change. He's also the director of the Goddard Institute of Space Science. And I was really shocked. I was discussing this with Gavin, and I was like, you know, it's going to be interesting when it gets cold again. And he goes, no, that's not going to happen. And, my jaw almost hit the floor. He's like, yeah, we're not going to have any more glaciers. And, fair enough. That's a bold statement to think that humans are capable of stopping this extraordinary pattern of behavior. But maybe he's right. Maybe we won't have any more glaciers if we keep things up the way that we're going. However, I do think that humans, while we're not necessarily addressing a lot of the pollutants, we do seem to have a grip on carbon, and we're working towards that. I know that California, for instance, is essentially outlawing combustion cars in the next couple of years. I think Oregon's moving in that direction eventually too, which is a huge sticking point for a lot of people because obviously the infrastructure is not there. It's not entirely clear also that we're getting electricity in the most clean way possible, right? Because the cleanest way to get electricity is through nuclear power. And people are terrified of nuclear power. They hate the word nuclear, which, fair enough. We've wrought terrible damage, and there's obviously the threat of us destroying ourselves with nuclear, but it turns out to be way safer than any other kind of power. And if you look at how many people have actually died from nuclear disasters in the power sector versus people who have died from emissions, right? From burning things, burning coal. It's not even a contest, right? Nuclear power is extremely safe. So what's causing this? Well, the word you'll hear pointed to a lot is this concept of Milankovitch cycles. Milankovitch was a Serbian geophysicist, an astronomer, and he did an amazing thing. He looked at all of the possible changes in the Earth's motion, and he looked at various indirect methods of observing these in the past, sediment levels and magnetic anomalies and excursions, and of course, all of the gas data that we have from the ice cores. And he deconvolved all of these, and then he put them back together. And this is what he came up with over here. It's kind of another anxiety-inducing graph, but we have the Vostok ice core, which we were just looking at the bottom. At the top, we have a number of different motions of the Earth, and we talked about a few of those. One of them is the axial tilt, right? This is also known as the obliquity. This is how much the Earth is angled. Right now, it's 23.5 degrees. That changes, turns out, over long periods of time. It wobbles a little bit. It's also the eccentricity. We talked about the eccentricity and how that's essentially very low for Earth. Well, it is right now, but it seems like in the past, the eccentricity has shifted a little bit. And this is thought to have actually to do with the pull of the bigger planets in the outer solar system, like Saturn and Jupiter. So the eccentricity has varied. And then there's also the concept of the precession, right? This is how we're pointing towards a different pole star at any given time. There's all of these factors. And what Milankovitch noticed was that there was overlaps, right? So much as if you wanted to take a piece of music, let's say, and you wanted to break it up into all of its constituent frequencies, you can also reassemble constituent frequencies and make a piece of music. And this is what Milankovitch did, essentially. He took all of these individual notes, which are these very predictable sine waves, and he saw that they summed up into something which he believed could collaborate to explain the Vostok ice core data. So he said, it's a convergence of all of these tiny motions that essentially result in the Earth getting more sun sometimes for longer, for long periods of time, or less sun for longer, and that this will repeat. And, it's a very, very elegant theory, and it checks out on a number of terms, but it doesn't work perfectly, right? There's this problem where Milankovitch, his calculations suggested that these periods should be actually a bit shorter than they turn out to be. And so while he might have been right in some sense in the greater picture, he was a little bit off in the details of it, and it leaves some room to think about what could be happening. So this is the seasonal ice cover, which is quite fascinating. It's very beautiful. Actually, one of my friends who's a geologist in Utah made this picture, and I'm going to talk about him in a second. But this is a very different ice cover than you get during glaciation periods. And this is my friend Lance Weaver. I actually put a link to the podcast with him in the notes for the class. I think some of you might enjoy that. In fact, this week you have to do a video response. So if anybody feels like listening to some of that podcast, it's a really cool conversation. But what and many other people have noticed is that the glaciers don't seem to be centered like that exactly over the North Pole. This is really, really bizarre, actually. They actually seem to be centered over Greenland. So what's up with that? Well, again, maybe this has to do with the convergence of all of those different types of motions that are slightly deviated from what we're used to today when we talked about the predictable motion of the Earth. Maybe it's a confluence of those events that's causing it, such that this particular part of the Earth is inclined away from the Earth. And maybe there's some truth to that. You know, Lance, and you can see this actually in the way that the glaciers have crept down into North America, right? The glaciers, have any of you seen these glacial fields before, like up in the north? If you go up to like Wisconsin, right, you can see these moraine fields. You can actually see very much how the ice pressed the crust down at these locations and crept outward. And what's really fascinating is that the glaciers weren't in Siberia, right? Siberia was temperate during the glacial periods. This is very bizarre. So again, the glaciers seem to be centered in a different point. And that's something really worth studying. I think this will be a huge topic of investigation in the next century, because I don't think that we totally understand what's happening here. You know, Lance advocates that perhaps the actual axial point of the Earth is bistable. There's like a mass imbalance in the Earth, right, where some of the material is slightly lopsided and some cosmic interaction is causing it to actually shift regularly at some point. So I highly recommend you guys check that out. This was a really good discussion, and I put it in the notes for the class. You know, I was going to talk a bit about calendars, but I think we're about out of time. So we'll talk a minute about calendars next time. It's all about the motion of the Earth, people. Everything that you see that's happening here, the weather, everything. And let's put a pin in it. Thank you, guys.